Hello, everyone. It probably helps if I turn my mic on. Sorry about that. I'm going to wait just another minute or so in case people are trying to get on, and then we're going to start with Section 8.1. Okay, let's go ahead and get started. This is actually, since we've already done Chapter 10, some of my classes I do 10 at the end, but for the face-to-face classes, I always like to do 10 with 1 through 3 like we did. And so since we've already done Chapter 10, this is our last chapter. We have 4 sections, and that is all the new material. After that, you just need to, do the homework, of course, for Chapter 8 and study for the Chapter 7-8 test, and then study for the final. There's nothing between. The way I had it scheduled originally, we did Chapter 9 between the 7-8 test and the final, but I've cut out Chapter 9. So all you guys have to do to finish all, and I know you're like, yeah, that's still a lot of stuff to do, but what's left is to finish Chapter 8 homework, study for the 7-8 test, and then study for the final. So I hope that I'm right about this. Hold on just a second. Let me share my screen. I didn't actually go and look at the note or at the schedule. If anybody has the schedule in front of them and I'm wrong, let me know. But I think what we have is, I think the Chapter 7-8 test is due not this coming Sunday, so not the 9th, but I think the 7-8 test is due the 16th. If I'm wrong about that, please somebody say so. But I think the Chapter 7-8 exam is due May 17th. It's the Sunday, whatever that Sunday is, I think. Not this coming Sunday, but the Sunday after. And then the final is due by May 22nd. Let's see if I can find that really quick. I think I have it right here in my file. I don't have to go to our class page or anything. So this Sunday, let's see, yesterday was the 3rd, so May 10th. You have the Chapter 8 homework. Well, I found it and it won't open. Come on, open up. I'm always amazed sometimes how your computer can connect to the internet and go to some random website, but it can't open a Word document sometimes. So anyway, that's what I think. It's May 8th or May 10th is Chapter 8, and then I think May 17th is the exam, the 7-8 exam, and then the final is it. You may want to try to take this early if at all possible, because you can do test corrections, but you have to do them between the 17th and the 22nd. So if you don't want to have to try to study and do your test corrections and all that, you might try to do your exam early. Now, it won't be available to do your test corrections till after the 17th, because I got to wait till people have taken it. but at least once it's available, you will have already started studying for your final, and you won't have all that to do in those 5 days. Yes, here we go. So we have our, yep, that's exactly right. So the 10th is your last homework. Yay, last homework. And then the 17th is your last chapter exam. And then the 22nd is your final exam. So does anybody have any questions on any of that stuff? You guys are quiet this morning. Everybody's tired of this, aren't you? Like, can we just go back to school?
I have a question.
Go ahead.
On our last test corrections, when are those due by?
Oh, Lord, I don't remember. I think it's shortly before that 7-8 exam, like the 17th or the 16th or 15th or something like that. Does anybody know? I didn't write it down anywhere except for putting it in D2L. Yeah, I think it's something. I think it's in the Dropbox. It says in the Dropbox.
Because I was looking yesterday and I couldn't find it, but I was probably looking in the wrong spot. Who knows? But I'll just assume the 15th and get them done today.
Yeah, I mean, so you have some time, but and I might be wrong. I might never have actually put a date in there. I may have just thought it in my head and not actually written it in there. But if I had written it in there, I would have said something along the lines of the 15th, because I want you to finish it, of course, before the 7-8 test, so you're not doing test corrections when you should be studying for the test. So that's what I would recommend. Do your chapter 8 homework, and then when that's done, do your test corrections, and then, or vice versa, and then go ahead and start studying for your 7-8 test. Oh, and the other thing too, I know you guys, a lot of you guys turned in your test corrections, and now you don't have your first test because it's sitting on my desk at the campus. So now you don't have that first test to use to study. And so I don't typically do this, but I think I'm going to write I usually tell people you could use your old tests and, you know, the old reviews. But I think what I'm going to do is I'm actually going to put together some sort of a cumulative review. So I'm not going to 100% promise that, because it's all based on how much, you know, if I have time to get to it amongst the other things that I have to do. But I would like to put together a cumulative review. If I can't do that, I will at least give you a blank copy of the first test so that you have it and you can go back and look at it. It's not really the same as having, and when I say blank, I mean, like, I'll give you the answers too. So like the first test along with the answers, but you won't have yours back. And that's better than nothing. But if I'm going to actually put something out there, I'd rather just put something together that's more focused on the final exam. So any questions on anything before we get going? Got hypothesis testing today. Okay, so let me go back, and I know I've said this before, and I'll probably say it again, but I'm going to go through this, the things that you have to recognize when you're looking at Chapter 8 and Chapter 7. So this is the outline for Chapter 8. Now, if we go back and think about what we did in Chapter 7, in 7.1, that was just the intro. Okay, and then 7.2, 7.3, and 7.4, we actually did the hypothesis testing, or not hypothesis testing, the confidence intervals. And so the confidence intervals, the first thing we did in 7.2 was we did a confidence interval for the mean, and that was with the sigma given. Remember, that's the difference between knowing which of the types of tests to use, is whether it's a mean or a proportion. And then if it's a mean, do they have sigma or only S? So first we did the mean with sigma, then we did the mean with only the sample standard deviation given, and then we did the proportion. Now when we did that, what did we do when we had the mean and we had the sigma? What did that mean? What kind of test were we doing, or what kind of confidence interval were we finding? What chart were we using?
The Z chart?
The Z, yeah. So this is important for you to, because on the test they'll be mixed up. I won't put them, I won't say this is one of these kind. There'll be these three kinds, but I won't tell you which is which. That's what you have to discern, is whether it's a mean or a proportion and which kind of mean it is. So this one, if it's a mean and they give you the sample standard deviation, you're going to do a Z. And if it's a mean with only the S given, then you do what?
The teacher.
The T. So this is the one where you go, let me put like a little note here. So on this one, we do the Z, which means we go all the way to the bottom of the chart. That T chart, that the student's T table or whatever that they call it in the book. I'm not sure what they call it, but it's not the Z chart, but the T chart, the one where it had the percentages listed at the top. But if it was a T, if it was a mean and we only had the S, then you had to do the degrees of freedom. You guys good? Okay, you're like, yep, we just did this homework last night. Okay, so, and then for P, we went back to doing Z. So you went all the way to the bottom again. Now, when we're doing hypothesis testing, it's the same thing. So here, they call this chapter, or this section 8.2, this is just an intro, again, just like 7.1 was. But then when we do 8.2, it's a Z test for the mean, and that's because the sigma is given. So we're doing a hypothesis test for the mean, and we're doing a Z test because they're going to give the sigma. And then this one, we're going to go back and do what they call a T test, because we're going to use the T chart, because only the S is given. So only the sample standard deviation. And then when we get to 8.4, we're going to be doing proportions. So we're going to be, this is a Z, this is a T, and then we do proportion, that's going to be a Z again, just like in chapter 7. So if you can remember it for chapter 7, it's the same thing for chapter 8, which is nice. It's not like, well, when we're doing this, you have to do it this way. It's the exact same thing. If they give the mean with the sigma, you do Z. If they give the mean with only S, you use T, and if they do proportion, it's back to Z. And it's the same for both chapters, for both confidence intervals and for hypothesis testing. In fact, confidence intervals can be used to do hypothesis testing. It's just a different way to do it that we're not doing. We're going to do confidence intervals, and we're going to do what we call in hypothesis testing the traditional method. So is everybody okay with this so far? Okay. So I'm going to do one more slide, and then we're going to take like a big, huge segue off on another topic, which will seem like we've completely gone off the road, but it'll help us understand what the heck a hypothesis test is. So the next slide that you guys should have, if you have your notes printed, is there's 3 methods to test hypotheses. There is the traditional method, which our book teaches. There's the p-value method, which our book also teaches. And then there's the confidence interval method, which our book doesn't really get into. Not only does our book not get into the confidence interval method, okay, so even though that's a possibility to do hypothesis testing, we're not going to do it. We're also not going to do the p-value method. So our book shows the p-value method, but I am not giving you any problems with the p-value method. I like to stick with just one method, because the point is that you understand a hypothesis test, not do you understand every single way in the world to do a hypothesis test. There's no need for you to learn all 3 methods simultaneously. It's, in my opinion, a lot nicer for you to just learn one method really well. And then if for some reason you took an advanced stats class and you had to use the p-value method, you'd pick it up right away, because it's not that different. It's just a little tiny different way of looking at the comparison numbers, and you'd pick it up right away if you understand the traditional method. So it's no big deal. And a lot of you won't take another statistics class. So there's no sense in making it more confusing, in my opinion. So our objective states that you guys have to learn hypothesis testing. It doesn't say you have to learn every method under the sun. So I like to stick with just the traditional method. So if you do watch the, I don't know if you guys have been watching the videos in Connect Math. Have any of you guys been watching those? The Connect Math videos too? A little bit. I see people who kind of say, eh. So if you do watch the ones for chapter 8, I think I have a note with it. But if I don't watch the p-value method. Once the video stops talking about the traditional method, it starts doing p-value method. Don't watch it because it's just going to confuse you for right now. Okay, so with that said, we're going to take a little sidestep here and talk about something that you guys are somewhat familiar with. Hold on a second, let me get a new. Something that you guys are somewhat familiar with just from living in the United States. We're going to talk about the criminal justice system in the United States, because we can then take it and relate it to what exactly is a hypothesis test. So we're going to talk about this, and then I'm going to that you kind of know already, and then we'll go back and compare it and talk about how each of the parts compares to a hypothesis test. So in the justice system, and again, we're talking about how things are supposed to work, not necessarily how they always do work. So we're going to be So if you guys want to flip your notes over or grab another piece of paper or just listen, it doesn't really matter, whatever you want to do here. So when you, in the criminal justice system, if you have people, or if you have someone who is suspected of a crime, then, and they're charged with that crime, what is our starting idea in our justice system? What do we think about that person who's been
And still proven guilty?
supposedly, right? And there's some argument that that doesn't always happen, but that's the premise, right? You're exactly right. So we are under the assumption, supposed to be under the assumption in our justice system, that somebody is innocent until proven guilty. Okay? Now, with hypothesis testing, that would be called what they call our null hypothesis. So H stands for hypothesis, and the little 0 down here stands for null, like 0. Why do we call it the null hypothesis? Because it's where we start. It's like the starting assumption. And so we start with that assumption, and then we build off of that. We say, if we can't, we're going to assume that they're innocent, and we're going to try to prove that they're not, or the prosecution is going to try to prove that they're not. Now, of course, the what we call the alternative hypothesis, or the alternate hypothesis, is that they're guilty, right? That they're not innocent. And I'm saying not innocent because that's kind of important. That's how we word things with the hypothesis testing, and sometimes it's a little confusing, but if you see it with this justice system that we're kind of used to, we often will say guilty, but what we're really saying is that they're not innocent. Okay? So our initial hypothesis, what we call our null hypothesis, is that they are innocent, and our alternative or alternate hypothesis is that they're not innocent. This is what you always start a hypothesis test with. You always have an H sub 0 and an H sub 1. And some books put an A here instead of a 1. Our book does 0 and 1. So this is like null hypothesis. This is the alternate hypothesis. But this is always our starting assumption, kind of our status quo, where, like our baseline, kind of where we start at. So now let's talk about what could actually happen in the trial. So you have on this side, you have your decision. See if I can write this. This writing tablet gets a little weird sometimes. But this is the decision, and then we have the actual. So really big question. When you take somebody to trial, does it change whether or not they were actually innocent or guilty?
No.
No. They were actually innocent or they were actually guilty before any of this started. You're not changing that at the trial. There's an actual real answer here. Like they actually did do the crime or they actually didn't do the crime. And I know there's, you know, does this fit into this definition types of things, but I'm talking about, you know, just think in your mind, you know, blatant. Did they rob the store or did they not rob the store? Did they hit the person or did they not hit the person? You know, just real straightforward. Did they do the crime or did they not do the crime? So there's something that actually happened. And by taking them to trial, we're not changing that. That's already done. So they actually were innocent. Or they were actually not innocent, which of course we sometimes would call guilty. Okay. And then there's the decision that's made at the trial. Well, the decision at the trial is that they're either guilty or they're not guilty. Which I always found weird because they kind of do opposite of how we word it. So finding somebody guilty is the same thing as finding them not innocent. Finding them not guilty is the same thing as saying, kind of saying that they're innocent. So let's talk about, you know, what decisions here are right and what are wrong. If you take somebody to trial that was actually innocent and you find them guilty, was justice served?
No.
No.
No. So this is an error, okay? This is an error. And this is something that, you know, we hope doesn't happen. We hope that we don't find somebody who was innocent guilty. What about if somebody was innocent and the trial comes back not guilty?
That
What's
would be, or that would be,
Justice has been served.
Justice has been served. That would be correct, right? Okay, so this is correct. This is what we want to happen. Yay, justice was served. They were innocent. They were found not guilty at trial, and they go on their merry way. Okay, so what about if somebody is guilty and we find them not innocent or guilty? Correct decision?
Justice has been served.
Justice has been served. This is correct, right? So this is a correct decision. So these two quadrants, innocent, found not guilty, not innocent or guilty, and they're found guilty, those are correct decisions. What about this one here at the bottom? What about not guilty?
Error.
That's an error, right? That's a travesty, what we would call a travesty of justice, because they were not guilty, or they were not innocent, they were guilty, and they were found not guilty. So you've got the two situations here. You've got an innocent person getting punished, or you have a guilty person getting off. Neither one of them are good necessarily, but in our justice system, what do we typically think is the worst error? Like, what does our justice system protect against?
is it someone innocent going?
That's why we assume that they're innocent until they're proven guilty. Now, not all government or not all justice systems in the world act like that. Our system is set up to protect the individual. Other justice systems are set up to protect the group as a whole. So they'll say, well, just the chance that they might be guilty, we're going to put them to jail because that's protecting the greater good, something like that. But in our justice system, we protect the individual, and we say that sending an innocent person to jail is a worse situation than letting a guilty person off. Okay, so this is in a hypothesis test. This is called a type 1 error, and in a hypothesis test, this is called a type 2 error. So a type 1 error is when you find somebody who is, or you have somebody who was initially innocent and you find them guilty. That's a type 1 error, and it's the one that we want to avoid the most. You can't always avoid it, but it's the one that you want to avoid the most. This one you still want to avoid, but it's not considered as bad. This is called an alpha, or it's talked about in the problem as an alpha, and this is called a beta. So this is like an alpha error and a beta error. The alpha error is what we want to avoid the most. Okay, so what do you guys think? So far, so good? Kind of okay? And this is stuff you already knew, right? Okay, so let's relate it, and I'm going to, in our notes, this is, on my notes, it's slide 15, so it's probably, it should be a little bit lower than that on yours, maybe 12 or something like that. Does anybody have it? Should look like this one.
11.
11. That was a pretty good guess on my part. Okay, so slide 11, we're going to go up and look at that, and then we'll go back to the other slides and start doing the hypothesis statements. But I really wanted you to understand what the heck we're doing before we start it, because I think it really helps understand how to do it. So compare this, what we just did, to hypothesis testing. So if we think the null hypothesis is true, but we reject it, that's a type 1 error. If we think the null hypothesis is false and we reject it, that was a correct decision. Or I'm sorry, if the null hypothesis was actually false and we reject it, that's a correct decision. If the null hypothesis was actually true and we do not reject it, that's a correct decision. And if we think it was false and we do not reject it, that's an error. So when we're doing our hypothesis testing, we are going to have the actual, okay, let me try to write this up here so it fits kind of what we have. So this is what actually the null hypothesis is true, or actually the null hypothesis is false. We don't change that by testing. Our test doesn't change that. It doesn't make it true or false. It already is true or false, and we're just trying to check it. Okay, and then this is the decision. So at the end of our hypothesis test, we make a decision to either reject or not reject the null hypothesis. And if it was actually true and we reject it, that's the worst type of error. If it was actually false and we reject it, that's a correct decision. If it was actually true and we do not reject it, that's a correct decision. And if it was actually false and we do not reject it, that's an error. So it fits exactly with the justice system. So now you're saying, what's a null hypothesis in statistics? Well, a null hypothesis is just something that people are assuming is true now. So it may be, it typically is from like a prior study. So they may say in a prior study, the average number of credit hours that students have after 2 years of college is such and such, okay? 40 hours. The average number of students, credit hours that students have after 2 years of college is 40 credit hours completed. That's a statement, okay? So when you start with a null hypothesis. And so in this case, you're saying, let's assume that 40 is what is the status quo, or the starting assumption, or the baseline or status quo or whatever. And then we start our hypothesis test by saying either we think that it's higher than 40, we think that it's lower than 40, or we think that it's not 40. So we decide before we start our study if we're checking to see if it's less than, greater than, or not equal to 40. So these are our choices here in the middle. You only have one of these at a time, but you could have any of these three. So this is what our null hypothesis and our alternative hypothesis look like when we start our test. That's the very, very first start of our test. And it's supposed to be done before any, data collection happens. You're supposed to say, oh, okay, well, it's published that this is the average. Let's see if it's not the average. Either we think it's lower than that, we think it's higher than that, we think it's not equal to that. And again, this could come from all kinds of places. It could come, you could say, the national average is 40 and we want to see if it's different at our college. You could say a prior study is 40. We want to see if it's still the same years later. So maybe this is 2010 and we're trying to check it against 2020. It could be a recent study and you're trying to validate that study. That's sometimes what they call peer-reviewed, one type of peer-reviewed. So when you have a study that already happened recently and somebody tries to check it and get the same results as you, that's also a way to do a hypothesis test. So you can do all kinds of things, but the main idea is that you have a baseline or status quo and you're trying to check it. So who is our person that we're taking, or our person that we're taking to court? It's our null hypothesis. So your poor little null hypothesis, he's the one that's getting taken to court. Okay, he is your what's it called? The person at court. I've lost it.
Defendant?
Yeah, this is the defendant. Thank you. I don't know why I couldn't come up with that. So your null hypothesis is your defendant. And sometimes your null hypothesis was just sitting there all nice and innocent. It is, the average is 40. Why are you accusing me of something? And you get done and you're like, oh yeah, okay, null hypothesis, you were right, it is 40. But your null hypothesis is like your defendant. And he's kind of going, oh my gosh, you're taking me to trial? Why are you taking me to trial? What are you going to find out about me? And then at the end, our decision that we make at the end is whether or not we found them guilty or not guilty. So when we reject the null hypothesis, we're saying it wasn't true. When we do not reject the null hypothesis, we're saying that the null hypothesis was true. So it's weird because we do this do not reject. I mean, what would you rather the opposite of reject be? You'd rather, instead of rejecting, accept, right? Like, why do they not just say reject and accept? And the answer is because we can't truly accept. Same thing over here. By saying somebody's not guilty, or we say that they're guilty or they're not guilty. We don't say they're guilty or innocent. I know it seems like a small thing, but the fact is we can never be perfect. So we're never going to say that we completely accept it. We're just going to say we didn't find enough evidence to reject it. So we do not reject. So this is what they're charged with. If you can kind of keep that in mind, it helps you, I think, as you go through. So the null hypothesis is like the defendant, and the alternative hypothesis is like the charge against them. We think it's less than, we think it's greater than, we think it's not equal to. That's the charge. And we're going to try to take them to court, take them to statistics court, and find out whether we think they're guilty, whether we should reject them or not reject them. So what do you, anybody have any questions before we actually go and start doing some hypothesis statements? Okay, so I'm going to get rid of this. Oh, by the way, you guys, there might be a little bit on your homework about type 1 errors and type 2 errors, but mostly we just do the hypothesis tests. And I don't think I ask anything on the chapter 7-8 test about type 1 and type 2 errors. This is more just an understanding thing. It's not, you're not going to actually be asked, is this a type 1 and type 2 error, except maybe a question or two on the homework. What you're going to have to do on the test is actually do a hypothesis test. Okay, so that's the objective. All right, let's clear this up. So before we go to the next slide, actually we can do this next slide. Okay, so we're going to go back to that slide that says 8.1 steps in hypothesis testing traditional method. This one. Now, I've seen people add in steps, but I'm not going to do that. I'm going to just stick with what our book does, and our book has 5 steps. So what we're going to work on in 8.1 is just the first step. And then when we get to 8.2, we'll actually do the whole thing. But let me tell you what the steps are. So the first step, this is only step 1 that they're talking about here. A statistical, whoops, I wrote that in the wrong spot. It's actually starts right here. So this is explaining step 1 right here. So a statistical hypothesis is a conjecture about a population parameter. Remember, a parameter is either the mean or the proportion. So it's a conjecture or a hypothesis about a mean or a proportion. And like we said, that conjecture, that hypothesis could either be true or not true. So the null hypothesis is the hypothesis that states that there's no difference between the parameter and the specific value, or there's no difference between 2 parameters. That's actually chapter 9 that we don't do.
You said the parameter is the mean and...
Yeah, parameter is like a general term for mean or proportion or standard deviation, but we're not doing standard deviation. So for our sake, the 2 parameters that you could have would be either mean or proportion.
Okay, got it.
And then the alternative hypothesis is the hypothesis that states the existence of a difference between the parameter and the specified value, or states that there's a difference between the 2 parameters. Again, this difference thing, that's chapter 9. We're not going to do that. Okay, so we're not going to do that, even though it is a way to do a hypothesis test. So what they're saying here is your very first step in a hypothesis test is to write the null hypothesis and the alternative hypothesis. That's step 1. And that's all we're going to work on in section 8.1. But I do want to lay out what the other steps are so you know where we're headed here, okay? The second step is to find the critical values or the critical region. Now, sometimes there's 1 critical value, sometimes there's 2. It depends on whether or not you're doing a less than, a greater than, or a not equals. And we'll get to that when we get to 8.2. Then we're going to have, in step 3, we're going to have the test values, or value, I should say. There is only just 1 test value. So you're going to have your hypothesis statement. Then you're going to find your critical values. Then you're going to find your test value. Then you're going to make a decision. That's where you reject or not reject. That's where you're finding whether you think that null hypothesis was guilty or not guilty. And then the last step is the conclusion. Really, once you get steps 2 and 3 done, you've done all the work. These, you just have to state what the work showed. So 4 and 5 are really quick. So the first thing is to get it set up right. Then you the critical values you get from the chart. Let me write that in here too. This is gotten from the chart. And then your test value is a formula. And then you compare the test value to the critical values to make your decision. Again, we'll do that, but just a real brief overview of what you do. Here's another kind of nice thing about this is if you go to your formula sheet, it actually has this listed in the formula sheet right here. Solving hypothesis testing problems with the traditional method. P-value method we're not doing. You'll see it's still got 5 steps. You compute test values, find the p-value, and compare those. You just find a different value and compare it a little differently, but it's still really the same process. So we're only going to do just this one, and it's right here on your card. Not only that, but on the test, it will say, write your hypothesis statement. What's your critical values? What's your test value? So you don't have to worry about, am I going to forget these 5 steps? Because they're going to be there. It's going to be outlined on the test. Tell me now what your hypothesis statement is. Tell me now what your critical value is. Tell me now what your test value is. What's your decision and your summary or your conclusion? So you don't have to memorize that necessarily. It's here on the card. It'll be outlined as you take the test, as you do your homework. So that's not don't worry about, oh my gosh, how am I going to remember all those, how am I going to remember the 5 steps? First of all, you're going to do it enough times that you're going to remember it. But secondly, it's all there. So that's a good thing too. All right, any questions on this before we try to do some actual hypothesis statements and see what they look like? Okay, so and I'm going to cut out just the part that has the problem and try not to put the answer up here where you can see it right away. Okay, so our first situation is that we have a medical researcher is interested in finding out whether a new medication will have any undesirable effects. The researcher is particularly concerned with the pulse rate of the patients. Will the pulse rate increase, decrease, or remain unchanged after a patient takes the medication? And the researcher knows that the mean pulse rate for the population under study is 82 beats per minute. So what do you guys think? What is our status quo, our null hypothesis?
82?
Yep. What's 82 though? What parameter are we talking about?
The mean.
Per minute.
The mean. So you don't want to just write the null hypothesis is 82. You want to write null hypothesis is that the mean is 82. So the average is 82. That's the status quo. That's where we're starting. So in this case, we're not questioning if that prior study or that average is correct. We're testing, does our medication change it? Again, there's lots of scenarios where you would be doing this. And so in this case, it's not questioning whether this is actually true. We're just questioning, does giving them the medication make it not true? Okay, so our null hypothesis is going to also have mean. And what are we trying to check here? Did they say that we're trying to check less than, greater than, or different?
Less than?
I thought it said all 3.
It does say all 3. So if it says less than, greater than, or different, or unchanged, that means that we want to check both directions. So we just want to know, is it different? So this researcher isn't contemplating whether it's going to increase the blood pressure or beats per minute or decrease the beats per minute. He wants to know either way. So he or she is looking at, is it changed? Does taking the medication change it? So when you're just trying to find out if it's different in any way, that's a not equals. If it specifically says less than, then you'd use a less than sign. If it specifically says a greater than, you'd use a greater than sign. But if it doesn't indicate either, or it says both, like this one does, this one says both, then you say not equal. That's our hypothesis statement. That's it. That's step 1. So if you were doing a hypothesis test, that would be step 1 and you'd be done. What do you guys think? You think you can do that? Okay, good. So a couple things to point out. This right here is always going to be an equal sign. The null hypothesis is always an equals. It's the alternative hypothesis that could be one of these. You have to make a decision as to whether it's less than, greater than, or not equal. But the null hypothesis is always equal. Another
So
thing, go ahead.
Okay, so since the problem had increase and decrease, is that how we got that sign?
Yeah, because otherwise
Okay.
we'd have to put a greater than, less than, like we'd have to put both of them in there, and that just seems
Okay.
silly. Yep. So since it said both of them, then we have to do a not equals. Another thing, you'll notice that this had an 82, and what's this number?
82.
82. These are always the same. So these two are always the same. Because when you do the whole thing, like when they do the whole hypothesis test, they have to then give you like the information from the study and such. But remember, if this was real life, the researcher would not have the study yet. They would write this out or state this before they did anything with the study, before they went and got, you know, any sort of research information. They would say, this is what I'm doing. It's kind of like a science experiment. You guys have taken, I'm sure, enough science classes, you know, even if you only took high school science, that you know that you're supposed to make your hypothesis before you do your study, before you do your experiment. You're not supposed to do your experiment and then say, oh, look, that happened. That was my hypothesis. That's what I thought was going to happen. It happened exactly how I thought. You can't do that after you've already done the science experiment. So before you do the science experiment, you make a hypothesis about what you think is going to happen. And same thing with the statistical experiment. So a test is kind of like a statistical experiment or a trial or whatever. You have to state this before you do anything else. So the researcher wouldn't know any other numbers except the status quo. So long story short, these two numbers are going to be the same. Whatever the null hypothesis is, the alternative hypothesis is going to be the same thing, but with a less than, greater than, or not equals. So let's see another one. Oh, don't let me forget to talk about left tail, right tail. I'll do that in a second, but let's do these first.
So what was that called then? Was it called, this is called a blank hypothesis test? What was it?
I'll come back to that. That's the left, right, and two-tailed. I'll come back to that, but don't let me forget about it. Okay, so a chemist invents an additive to increase the life of an automobile battery. The mean lifetime of automobile batteries without the additive is 36 months. So again, this isn't necessarily saying that the prior study was wrong. It's just saying this is what the study has. Is my additive changing it? So the additive is kind of like a medication or whatever. So what's our null hypothesis? Again, this is the first step in the process.
Mean equals 36.
Yep, perfect. So you guys got this already. So the mean equals 36. That's our starting status quo baseline assumption, that the mean is 36. What is this researcher, this chemist, hoping will happen or checking to see if happens?
Is it
Increase.
A lot.
Perfect. So a chemist invents an additive, and the additive is supposed to be to increase the life. So this would be, are we going to use a greater than, a less than, or a not equals?
Greater than.
Greater than. Yep. So the researcher, the chemist, wants to know, will the additive increase the mean higher than 36? Will it make the battery last longer? So again, you notice this one's an equal sign. Always, always, always an equal sign. And then for this one, we had to decide whether to do greater than, less than, or not equals. And we did greater than because it was an increase. That's it. So let me do one more. So the next one talks about this contractor. And it says a contractor wishes to lower heating bills using a special type of insulation. If the average monthly heating bill is $78, what is her hypothesis about the heating costs? That one was worded kind of weird. Okay, anyway, what's her null hypothesis going to be?
78.
78. Oops, I'm trying to get off of the red here. Oh, come on, computer. Okay, so the null hypothesis is that the average is 78. Don't forget you have to have average there, okay? What's the alternative hypothesis?
Is it decrease? Or,
Is it less than because it's lower?
Yep,
Yeah.
you guys are right. So because the contractor is hoping that this insulation lowers the heating bills, the average now is $78 a month. You don't have to put the dollar sign in there. I'll put it in there just to kind of for discussion point. So the average is right now $78, and they're hoping that the insulation will lower that heating cost. Dang, I wish my heating bill was $78. Okay, anyway, here I guess it's not really the heating bills, it's the AC bills. What do you guys think of those? Do you feel like you are doing okay on those? That's step one every time. So step one, you're always going to do this.
I mean, it looks like the word problem gives us like the answer to it.
As long as you remember that's your first step. You're right.
Yeah.
You just have to kind of look for those key words. But remember, these two numbers are always the same. And this is always going to be an equals, and this is going to be a less than, greater than, or equals. I think on your homework, like here, it will give you equals, less than, greater than, not equals. So you need to realize every null hypothesis is going to be equals. Even though they give you all four choices, it's always going to be equals. And then here, it's not ever going to be equals. It's going to be one of the other three. It's going to be a less than, greater than, or not equals. But I think on your homework, they give you all four to choose from. Like I think it's a drop-down menu if I remember right. Okay, so now let's not forget what Leo was asking about. So the other thing that it says on your slide is, so this is called a blank hypothesis test. So on situation A, this is what's called a two-tail test, and then the other ones are called one-tail tests. And why is that? Well, if you think about this, you have your 82 as your mean, right? And you're saying, did I go this way or this way? Either one. Like, it could go down or it could go up. I just want to know if it's different. So you went towards the left tail of the normal curve and the right tail of the normal curve. So this is called a two-tailed hypothesis test. And it's very similar to our confidence intervals, because the confidence intervals always go down and up. But with hypothesis tests, you can choose to only go down or up. So it'd be like just doing one side of a confidence interval. And that would be the other two scenarios that we had here. So if you go just down or just up, we call that a one tail, or you specify right, left. So in this case, I just want to know if it got bigger. And so this is called a one-tailed right, or just a right-tailed hypothesis test, because we're only worrying about whether we're going up. And what this matters for is if it's one tail, you only have to find one critical value. If it's two-tailed, you have two critical values. Again, we'll find that all on the chart, but you got to know whether it's one tail or two tail before you look at the chart. And then down here, what do you guys think this one would be?
One tail to the left.
Yep, you got it. So this is one-tailed left, or more simply, just left-tailed. So you have your average in the middle, which from the chart, we'll call that 0. And then you're going to look if you got high enough or low enough. So basically what we're going to do is we're going to check and see if the standard deviation is so big that we get way down in the tail. If we get way down in the tail, that means it's very unlikely to happen. and that's when we reject. But we'll talk about that more when we get to 8.2. What do you guys think about, okay, so just to summarize, a not equals is going to be always going to be two-tailed, and a greater than or less than is always going to be one-tailed. Greater than's one tail right, less than's one tail left. So far, so good? Okay. All right. Let's look at I think a lot of this we already covered because we talked about it when we were talking about the study. Just a second. Okay. So when you're doing a hypothesis test, the researcher has a claim. Come on. And what they're looking for is they're trying to decide if they have evidence to support their claim. So if you think about the insulation one, not the insulation one. What was the second one?
A chemist invents
The battery. Okay, perfect. So if the claim of that chemist was that their additive increased life, that's their claim. So the claim is what they think might happen, and they're trying to find evidence to support it. Now, it doesn't necessarily always have to be a good thing. It could be something that they're concerned about and want something done about, or it could be something like the chemist is hoping. You know, they really hope that the additive improves the life of the battery. But you have this claim, and that's usually the alternative hypothesis. So therefore, the claim should be stated as the alternative hypothesis. Then it says the claim, though, can be stated as either the null or the alternative. However, statistical evidence can only support the claim if it is the alternative hypothesis. So, long story short, this is not good practice. It is not good practice to have your claim be your null hypothesis, i.e., you will see no problems of this type. Again, if I'm going to teach you guys something, I want you to actually understand what you're doing, not just try to figure out, you know, oh my gosh, there's 5 different ways, which way am I doing, blah, blah, blah. I want you to understand that what we're doing is we're testing a null hypothesis against a claim, and this is how you test it. If you have to do anything beyond that in other classes, if you have a good basis of it, you'll be fine. So I don't want to show you bad practice. So we're not going to have any problems like that. There's not going to be any problems where the null hypothesis. So when you're doing your homework, again, there's going to be a drop-down box. It's going to have like mean, equals 36. Do the same one with the battery. Mean greater than 36. And then over here, it's going to ask you to pick whether this is the claim or not the claim. And then it's going to have a drop down for claim, not claim. So which one is always going to be the claim in your assignments?
H2 or?
Yep,
Yeah.
H sub 1, the second one. Yep. So this one will always be the claim. This one will always not be the claim. So you don't even have to worry about that. And I don't even ask it on the test. I just can't take it out of the homework. So on your homework, every time the null hypothesis will not be the claim, the alternative hypothesis will be the claim, because I didn't include any of these. I don't see any point in showing you guys bad practice. If it's not the right way to do it, let's not do it that way right now. Okay, so when we are hold on one second. So after we state the hypothesis, the researcher's next step is to design the study and they select the correct statistical test, choose a level of significance, and formulate a plan. So this is what we'll do this in 8.2. Select the correct test. That's whether or not you're doing a Z or a T. So if it's a mean with a proportion, with a standard deviation of the population, we'll do a Z, or if it's a proportion, we'll do a Z. And then if it's a mean without sigma, if we only have the S, we'll do a T. And then the level of significance that will be given. The researcher has to choose it, but for you guys, it has to be given because you have to be able to do the problem. So level of significance is going to be given, and then that'll tell you where to go on the chart. Like I said, a lot of this we already talked about when we were talking about the comparison to the trial. So, the statistical test or hypothesis test uses the data you take from your sample to make a decision about whether or not the null hypothesis should be rejected. And it's done by finding this test value. And then there's 4 possible outcomes, and we already looked at those. So the 4 possible outcomes was the slide with the 4, like the checkerboard looking thing. Hold on one second. So to fill in your slides. So in reality, the null hypothesis may or may not be true, and the decision is made to reject or not reject. You get that type 1 error if you reject a true null hypothesis, and you get a type 2 error if you reject the false hypothesis. If you don't reject a false hypothesis. And again, this is all just saying in words what we already talked about on that slide. Does anybody have any questions about any of that?
Wait, so type 1 error is when you reject a null when it's true, right?
Right. So let me just put this up here, even though we looked at it already. I will not ask you this on the test, but it might be on the homework. So a type 1 is that one that's considered more serious. It's when the null hypothesis was actually true. So again, think of it like your defendant. The null hypothesis is sitting there, and he's like, I'm just sitting here doing nothing. I wasn't wrong. I wasn't lying. I'm true. Why are you accusing me of this? And yet when the trial is done, you reject it. And he's saying, I'm not guilty. I'm true. I promise I'm true. And you're like, nope, I found evidence. I'm going to reject you. Get out of here. That's considered a type 1 error when it was actually true and you reject it. Does that make sense?
Yes, ma'am.
So this is like you didn't find, like you found enough evidence to prove it wrong, but it really wasn't wrong. And that happens in a trial. That's where you say, you send that innocent person to jail. So a null hypothesis, this is like a little innocent null hypothesis. It was true. He was innocent. And you found him, you rejected him, found him guilty, and that's the worst kind of error. So that's actually a great question, because then this next slide talks about the alpha and the beta. So when you have a type 1 error, that is the alpha. So the chances that you're going to get a type 1 error, the probability that you're going to get a type 1 error, that's the alpha. And then the probability that you're going to get a type 2 error is called the beta. They don't give the beta in the problem. We don't deal with that. This is what they're going to give. So they're going to tell you in the problem, alpha level 5%, alpha level 10%. So this is like with our confidence intervals. Remember, we would say we have we are 95% confident that it's between here and here. That would be the same thing as saying, I'm going to allow an alpha of 5%. So with confidence intervals, we say the chances that we're right. With a hypothesis test, we list the possibility that we're wrong. So here, confidence intervals, we say we are 95% sure we're right. With a hypothesis test, it's the same thing. They just word it backwards. They just say there's a 5% chance that we're wrong. But they mean the same thing, basically. So this is that we might not catch that actual mean, and this is that we might test and find the wrong answer. So the alpha is going to be given in the problem. Did that answer your question? Probably answered your question and beyond, but hopefully, does that make sense?
Yes, ma'am.
Okay. So typical significance levels, and this one is nice. They have to have it on the chart because we're not going to go back to the Z chart for these. Let me clear this up. Has everybody got all this written down? Can I clear this? All right. Speak now or forever hold your peace. Okay. So typical levels when you're doing hypothesis tests is for an alpha to be 10%, 5%, or 1%. So if you say alpha is 10.10, that means there's a 10% chance of rejecting a true null hypothesis. So 10% chance of rejecting a true is a type 1 error. I keep saying error instead of error. So we have a 10% chance of committing a type 1 error in our test. And of course, the higher chance you want to be correct, the higher chance that it won't happen. In other words, it makes the beta higher. So if you make the alpha higher, it makes the beta, if you make the alpha lower, it makes the beta higher. So there's all these things that the researcher has to decide before they do their test as to what's most important to them. All right. Where does 8.2 start? Oh, there it is. Okay, so we're going to look at, I lied. I forgot that in 8.1 they also do the critical regions. So we're now going to talk about finding the critical regions. This is step 2 of a hypothesis test. I thought they didn't do that until 8.2, but I was wrong. Okay, so a critical region or rejection region is that range that indicates that there's a significant difference between the null hypothesis or between the hypothesis statement and the alternative statement, and we're going to reject the null hypothesis. The non-critical region is the range of values that indicates the difference was probably due to chance. So what we're saying is when we do a study, if we get a critical region or we get a value that's in here, we're going to say, oh, yeah, it's a little off of what the null hypothesis was. Our sample was a little different than the null hypothesis, but it wasn't so different that we could say that these two things are actually different. It's probably just because I had a sample and that was a different sample. So if we get in the center here, we don't worry about it. We just say, you know, the null hypothesis was probably right. We just had a different sample. But if you get down in these areas, this would be for a two-tailed. So a two-tailed you'd have on both sides. And a one-tail you'd have on either the left or the right. So this would be a less than or a greater than. But you're going to have a value here, and if your test value comes out in these little areas up here, we're going to say, wait a minute, this isn't just chance. This isn't just because I had a different sample. something really is different between these two between these two samples. Between what we had before and what I have now, something has to be different. You know, the batteries are lasting longer. The insulation is making your the costs go down. So the medicine is changing the heart rate. So if they end up in here, that's your critical region, and that's when we reject. So these are called your critical or rejection region. So this is where you reject the null hypothesis. And I always tell students, you know, just silly stuff to help you remember it. I mean, there's nothing wrong. In fact, it's good to be silly with stuff. If you think of something that's silly but it helps you remember it, then use it. So in this case, I always tell students, if you're if you're, you know, make it down here and you have to go into this dark little cave, if you're in the deep dark cave, that's when you're going to reject. So if we're in the deep dark scary little dark cave, we reject. If you're out here in the sunlight, we're good, we're going to not reject. But if we get down in here, we're going to be, no, I don't want to be in that dark, scary cave. So that's the rejection region. That's the scary rejection area where we say, no, something's actually different. So the critical value is going to be the number that we put here, and it's going to separate the critical region from the non-critical region. So we're going to figure out that critical value in step 2. And then in step 3, we figure out whether or not our test value is in there or not in there. So let's look at how do you find those. So again, they're jumping into the middle of the process here. This would be step 2 when you're doing your test. Say you were doing your test and you needed to find, you were doing a right-tailed test. So you had a null hypothesis. If you had a right-tailed test, that means your null hypothesis had a greater than sign in it, right? And if the problem said it was an alpha 0.01, then you would look, oh, and you're doing a z-test, then you would go to the chart and you would look on your chart for alpha equals 0.01 right-tailed. How do you do that? Grab your chart if you have it. If not, I'll pull it up here. You go to the T-chart, and you'll notice, you probably didn't pay much attention to it before, but you'll notice it says 1 tail, 2 tail, and then it has the degrees of freedom. That's only if you're doing a t-test, which we're not, we're doing a z. So we're going to go all the way down to the bottom, and we're going to look at the z, but we're going to make sure that we do it for a 1 tail alpha 0.05. You guys okay with that? It was a, let me see if I can, it was alpha 0.01 right-tailed. So alpha 0.01, I said 5, sorry. Alpha 0.01 right one-tailed. So 1 tail, 0.01, go all the way down to the bottom. So it's this number right here, 2.33. So it's really just like you were doing for the confidence intervals. You just have to decide if it's right, left, or two-tailed, and then whether it's a Z or a T. So in this case, where's it at? There we go. So in this case, oh, see, they're using the Z chart. You don't have to use the Z chart. Use the T chart. And you're going to go to 1 tail. Then you're going to look over to 0.01, and then you're going to go all the way to the bottom. And you get 2.33. Okay. Now, what I always tell people is at this point, I don't check it. Like, it's not part of what I check as right or wrong, but I would absolutely draw this picture after you get this number. So draw yourself a little picture. Here's 0. Our critical value is 2.33. which puts our dark cave up here. Somebody had a question. I talked over them. What did you say?
I was gonna ask, whenever you got the 2, 3, 3 from the chart,
Mm-hmm.
so I don't know, I was wondering how you got that, because I was looking at, if you go all the way down, it's 2.326. And
Our
that-
book it puts it in the chart to 3 decimal places, but then in all the homework, it only takes it to 2.
Well, because on my chart, it has it at the bottom as 2.32, and then right above that is 2.33.
Right. So I'm looking at the very, very bottom, the 2.326, but I'm
Okay.
just rounding it to 2 spots. So 2 rounds up to 3 because there's a 6 after it.
Right.
So
Okay.
that's where I got that from. It's not from this one. I see where the confusion was. It's not from that one. It's from this, but I rounded it to 2 spots. So it actually says it right here too. It says this value has been rounded to 1.28. This value, so this one right here, 2.326,
Mhm.
has been rounded to 2.33 in the textbook.
Okay, great.
So
Thank
yeah, and that's what they
you.
do in the homework. And I'll tell you what, on the test, if you're not going to mess it up, because I'm going to give you, like, the choices for are going to be like these. And so if you see, it's going to be either 1.28, 1.65, 1.96, 2.33, or 2.58. Well, you're not going to pick, you're going to pick the one that's the closest. You're going to be like, oh, well, it's supposed to be 2.326, and my only choice is 2.33. I better pick 2.33. Does that make sense?
Yes, I didn't even realize that you had to round it. I'm sorry.
Yeah, they did that in chapter 7 also. So this is step 2 of our process. So what we just did is step 2. This is finding the critical value. Okay, so we found the critical value 2.33, and we found that the critical region was above 2.33. Again, we haven't done step 3 yet. Then there'll be a step 3 where we check it, but that's just finding it. So let's find another one. Well, this one's actually kind of goes with the one that we just did. So let me leave that on the screen. So this one says, find the critical value for alpha 0.01 left-tailed. So let's look at our chart. So we still have, it's still one-tailed. It's still alpha 0.01. And it's left-tailed, which is also a one-tailed. So if we go to the chart, where does it do the left at? Well, it doesn't. It just says one tail. It doesn't say left or right. So if it's left, we still go to 0.01. We still go all the way to the bottom, and we still get 2.33. So what's the difference?
It's negative?
It's negative. Perfect. So we're going to go like this because it's left-tailed, and it is 2.33. It's just negative 2.33. So they're saying, hey, we don't find the need to clutter up our chart by doing left and right, since they're just opposites of each other. So we're going to give you the right, and if you have a left, just make sure you put it as a negative. That's why this picture really helps. Left-tailed, that would mean in the problem, your null hypothesis was a less than. And so you're down here, not up here. And then as you can guess, the next example is going to be a two-tailed example. So this one says, let's find a critical value for alpha 0.01 two-tailed. So find the critical value for alpha 0.01 two-tailed test. So we go here, and we go up to the top, and we can't use this row anymore. We've got to use the two-tail row. So I'm going to use the two-tail row. This time I end up going all over to the very last column instead of the second to last column. I go all the way to the bottom, and it's 2.58. The difference is you're doing like an alpha over 2 now, because you're splitting it between the two ends. So a 1% or a 1% is like a 99% confidence interval. See how they match up? Since you're going both directions, it's just like a 99% confidence interval. A 1% error is the same thing as being 99% sure. So they match up. But you don't have to worry too much about that. All you have to do is one-tailed, two-tailed, and then, you know, find your value. But that's why you have to shift over a column. It shifts over a column. So it's 2.58. So 2.58. But this is two-tailed, right? So in our picture, how many critical regions do we have?
2.
2. It's here or here. This researcher wanted to know if it went down or up, if it changed in any way. So they're going to use 2.58 negative on this side and 2.58 positive on this side. So if their test value comes out above 2.58 or below negative 2.58, then they're going to reject it. Again, in every single one of this would be step 2 of your hypothesis test. You would have already done your statement, and then you'd be doing finding your critical value. So these would all be step 2s of the hypothesis test. And now I think we are actually. So now they're going to show the easy way, which we already did the easy way. But let's just practice it really quick. So if you have a chart with you, let's just do these really quick. I think I'll just write them instead of clipping them. It'll be faster. So it says, okay, now that we kind of have the idea. Well, actually, they did the hard way first. So, but now that we have the idea, let's try a couple more. So what if it was a left-tailed alpha 0.10? What would your picture look like? Left-tailed 0.10. Pull up the chart. So I'll kind of try to scroll here so you can see. So left-tailed 0.10. What would your answer be?
1.28.
You guys see where he's getting that from? So what do you look
Yes.
at up here?
The one tail.
The one-tailed 0.1. Perfect. And then like when I said, you'd go all the way here and you get 1.28. But it would actually be
Negative 1.
negative. Yep, because it's a left-tailed. So good. So 1.28, but since we're down here, it's negative because this is 0. So your critical region would be anything below negative 1.28. Okay, let's try another one. The next one says, what if it was two-tailed and your alpha was 0.02? What would your picture look like? What would your critical values be? Two-tailed alpha 0.02.
2.33.
2.30. 2.3.
Yep, perfect. You guys got it. So two-tailed 0.02s right here,
Negative and positive.
and then go all the way to the bottom, and you've got 2.33. And then I think I heard somebody say you have to put if it's two-tailed, you have to do both of them, right?
One negative.
Wait, so do you put equals positive or negative 2.33?
I just put it in the picture because when I do it without the picture, I always make a mistake. Not always, but more often. I'll forget it's two-tailed or forget it's left or something like that. So yeah, you could write as an answer, you could say the critical values are positive, negative 2.33, or I just put it in the picture.
And most of the time, it will be to the left of that's like really low, right? In the cave, like you said.
Yep, we're looking to see, we'll reject if we end up here or here. So if
Okay.
our test value, we're going to have a test value for third step. And if our test value is smaller than negative 2.33 or bigger than 2.33, we reject.
Okay.
But it's out here in the daylight, we're like, yay, happy day, everything's fine. Well, actually, that might make the researcher mad. But anyway, still you couldn't send the null hypothesis to jail. That's like a prosecutor being mad because they couldn't come up with enough evidence. But it happens, and that's the decision, and then you have to go with it. Okay, so if it was right-tailed, alpha 0.005, last but not least, what would that look like? So right tail, alpha 0.05.
2.58.
You are correct. So you have to go to one tail, right? 0.005, not 0.05, 0.005, and that'd be 2.58 again. You end up using those same values kind of over and over. So it's right-tailed, 2.58, and you would reject if you were up here. But this picture is so helpful. It's not checked on the test or anything, but I would absolutely draw this as you're doing it, because then you can see your rejection region. You know you're not forgetting the left-tailed, right-tailed thing. Your brain likes a picture so much better. So make this little picture. Just takes a second. It doesn't have to be beautiful. It's just for you. Okay, so now what we're going to do is we're going to learn what the formula is for the test value and actually do one of these hypothesis tests. I think you'll actually breathe a sigh of relief when we're done. It's not as bad as you think it will be. And this is it. Once you understand a hypothesis test, that's our last topic. All you have to do is learn the little subtle differences between a Z and a T, and you're set. All right. So this is the formula for the test value, and it's going to look really familiar. Does that look familiar? To find the test value, you do x bar minus mu over sigma over square root of n. Does that look familiar?
Yep.
That's the same thing we used for
Chapter 6.
Yeah, it was in
The
chapter
central
6.
Central limit theorem.
There you go. Thank you. I don't know why I can never remember the name of that. It doesn't make, for some reason, it doesn't fit what it is. I want to call it like the sample theorem or something like that. But it's when you have a sample instead of an individual. And that's what we have here. We have a sample, and we're testing to see if that sample is unique enough to reject or not reject. Another thing, this is called hypothesis testing. You've probably heard this before. You've probably heard the term statistically significant. So if it's statistically significant, that means you rejected the null hypothesis. So in a study, if it says the difference was statistically significant, that means that they found the difference between the prior study and their study, or the status quo and after their drug was significant enough to say it's different. What you'll hear sometimes you'll hear crazy stuff like, oh, in our district last year, our test scores showed that, 72% of our students passed this test, and this year 73% of our students passed the test, so we've improved. And you're like, wait, is that really an improvement? They really can't just say because these two samples, one was bigger than the other, that it's better. You have to test to see if that's a statistically significant change. So they shouldn't be saying it improved without doing a hypothesis test, but they do all the time. So they should not say just because it went up by a percentage that it's better. They should test the new sample against the old sample, see if it's statistically significant, and then say, statistically, it's unchanged, even though it shows 73%. But again, you'll hear people that don't know anything about statistics are given the task of analyzing statistics, which is never a good thing. All right, so jump off my soapbox now. You guys ready for an actual one?
Yep.
All righty. So I'm going to go through this like agonizingly slow. Hopefully you guys are okay with that. We may not get all of these done because it's already 11:30. I don't want to keep you guys too much after that. But we've done like so much of the bulk of the work for hypothesis testing already. Now we just have to practice it. So we will definitely get through 8.4 on Wednesday, even if we go through this one really slow. So I want to make sure that this makes sense to you guys. All right. So before we even read it, what are our steps? Step 1 is
Identify the mean.
identify the
Identify the mean.
kind of. What did we call it though?
It's a null hypothesis.
Yep, the null hypothesis and the alternate hypothesis. We're not going to do it yet. Let's just write it out. So step 1, we'll do the null hypothesis and the alternative hypothesis. Step 2, we're going to find the,
Critical values.
yep, we're going to find the critical values. I'm going to do a whole complete hypothesis test here. So we'll do the null hypothesis and the alternative hypothesis. Then we'll find the critical values. Then we'll find the test value. And then we'll make a decision and a conclusion. Really, these just, I mean, they put them as 2 separate steps, but your decision and your conclusion are just based off of, you know, what you find, whether we're in the critical region or not. So for the decision, I always give this already filled out. And so what your decision will look like is it'll say something like, so we blank the null hypothesis because blank. It'll might have a little bit more around it, but that's basically it. And then the conclusion is there blank enough evidence to support the claim, whatever the claim was, okay? So all you have to do for the decision and the conclusion is fill in 3 blanks. This one will either be reject, not reject. Here, we'll put it right here. This will be reject, not reject. This will be because we're in the critical region or we're not in the critical region. And this will be there is or is not enough evidence. So we'll get to those at the end, but that's the only decisions we have to make. Reject or not reject, in critical region, not, is or is not. So let's go, and we haven't even actually looked at the problem. What does it say? In Pennsylvania, the average IQ score is 101.5. It's normally distributed, population standard deviation is 15. We actually don't even need that. A school superintendent claims that the students in her class, we don't need the standard. Well, I guess we do. We do need that. Here, let me do that different. We do need that. We just don't need it for the hypothesis. But anyway, a school superintendent claims that the students in her school have a higher IQ. She selects a random sample and finds the mean to be 106 and tests that claim. So, starting with this, what is the null hypothesis? The status quo, the assumed baseline.
101.5.
And it's a mean, right? So the assumption is that that IQ is 101.5. Okay, what does this superintendent think?
It's higher.
She thinks her students are higher than that.
So increase.
Whoops. Yep, so greater than. Again, this is always going to be equals. This is always going to be greater than, less than, or not equals. And we did greater than because she said higher. Okay, so now we have to find critical values. So tell me what in here I'm going to look for so that I can go to my chart and find the critical values.
So it's greater than 101.5. So doesn't that mean it's left? No, right?
Yep, right-tailed. So when I get done, I'm going to have a region up here, right? What else do I need to know?
It's the 0.05. I think.
Yep, alpha's 0.05. This is a typo. It should be alpha.
Yeah.
Somehow the slide didn't get the Greek letter. So it's supposed to be test the claim at alpha 0.05. So right tail 0.05. And before we do it, we know this is is a z-test because it's in section 8.2. But if it was on the test, how would you know it was a z-test? If you're doing one where they were all mixed up. Yep, they gave you the population standard deviation, right? They gave you the sigma. So because they gave you the sigma, you can do a z-test, which is great because we don't have to worry about degrees of freedom and all that. So we're going to go to the bottom of the chart, or we're going to go to our chart. Right-tailed 0.05. This one.
1.96.
You go all the way to the bottom, and no, you're 1 over too much.
Yeah, it's
You did-
1.65.
Yep, I think you did two-tailed 0.05. Yep. So 0.05 one-tailed is 1.65. You guys okay? So we went one-tailed 0.05 all the way to the bottom 1.65. You guys okay with that?
Mhm.
All right. So we draw that in our picture. So 1.65. Whoops. Not Z, but. So because that's so small, I'm just going to write it over here too. But that's supposed to be a 1.65. Okay, now we just need to compute the Z. We need to decide, am I in the rejection region or not in the rejection region? So what's the X bar?
Sample mean.
101.3.
Is it the 101.5 or
It's 106.4.
106.4? Because this is the sample average, right? The X bar. We know the mu is 101.5. That's why that's right there. Ooh, I just lost everybody's face. Are you guys still there?
Yeah.
Yeah, okay. I was afraid maybe I lost internet connection or something. So we already know mu is 101.5, and then my internet went out the other day. I about had a panic attack. Okay. And then what's the sigma?
15.
Standard 15.
Okay. And then what's the n?
30.
30 student.
30. And then we just have to compute this. So I always do the bottom, and I always write down what the top is, then compute the bottom and do divide by answer. So this is 4.9. And so then I would compute this and then do 4.9 divided by answer. But however you do it, as long as you're doing, following order of operations and such, what do you guys get from that? I'm going to cheat and look at the slide. So somebody throw out, be brave. What'd you get?
My answer was 1.79.
Yep.
I got 1.81.
You probably rounded something.
Yeah, I think I rounded the square to 30.
And I wouldn't do that.
Okay.
I would try to leave that in your calculator. So if you have the square root of 30 first, then do 15 divided by answer, it equals,
Okay.
and then do 4.9 divided by answer. You can also do this all at once if you don't mind typing in the parentheses. I just hate typing in parentheses.
Mhm.
You can do parentheses, this minus this parentheses, divided by parentheses, this divided by that parentheses. But you should get about 1.79. Okay, so now what's our decision? Is 1.79, let me write this in a different color so we can kind of keep track of it. So this came out to be 1.79. Where is that? Is that down here below in the non-shaded part, or is it up here in the deep dark cave?
above in the deep dark cave.
The deep dark
Yeah.
cave. I know it's silly. You guys can laugh at me later. Okay, so we're up here, right? 1.79 is above 1.65. So it's up here in the cave. It's not that much into the cave, but it is. And so we're up in the critical region, the rejection region. So the decision is we are in the critical region. So what do you do when you're in the critical region? Reject?
Not reject. Not
We
reject.
don't. Re-
No, we
no.
do reject.
we re-
We do. This is called the rejection region. So if you end up in the rejection or critical region, then you are going to reject.
You're rejecting the offer to go in the cave.
There you go. Say, no, I don't want to be up there. So you're going to reject because you are in the critical region. And so there is enough evidence to support the claim that her students have a higher IQ. There is enough evidence to show that her students, remember this is her claim, so we've rejected the null hypothesis, which means her claim is true, or quite likely true, that her students have a higher average.
So whenever you reject, it's
When you reject the null hypothesis, that supports your claim,
okay.
because it means the null hypothesis is not right, or we
Okay.
think the null hypothesis is not right, so your claim must be right. They can't
Okay.
both be right. The average can't be 101.5 and greater than 101.5. Again, in this case, we're not saying the 101.5 is wrong. We're just saying that the group we're looking at is different than that. So we're saying our group is different. Our group is not 101.5. Our group is better. Little thing to note here, though. If you reject, it's because you're in the critical region, which means there is enough evidence. You notice those are all positives. Reject, in, is. What if we did not reject? Ooh, that's not good color.
Would it not fit in the cave region?
Yeah, if we not reject, it would be because we were not in the critical region, and so there would not be enough evidence. So it's either all positives or all negatives. So it's either reject because we're in, because there is enough evidence, or we not reject because it's not, and so there is not enough evidence. So they always go together. Once you have the reject, then it should be in and is. And if you have not reject, it should be not and not all together. The only way that those get mixed up is if you do it the way that we're not going to look at, that bad way where you do your claim on the first one, which we're not going to have. So you won't see that. So for all of ours, it's going to be reject because we're in and there is enough evidence, or not. So do you guys want to do one more, or do you want to call it a day and work on your homework? And what do you guys think? You want to do one more?
One more, please.
One more, please. Okay. And we'll do the other ones on Wednesday. I just think.
So
I
if we
think
did reject, it would be in the sun, like the sunlight part, right?
Yep. So if it's in the sunny, if it's in the bright, the white part, the lit up part, we not reject. We're like, everything's good with the null hypothesis. We didn't find enough evidence to send him off to statistics jail. Okay, so this next one, they actually gave some raw data, but we're not going to have, the homework won't have any raw data. So I'll throw in the extra info that we need. So, new file. Here we go. Okay, so this is the same principle. It says for a specific year, the average score on the SAT math was 515. The variable is normally distributed. Population standard deviation is 100. The same superintendent wishes to see if her students scored significantly below the national average. She randomly selects 36 scores, and at alpha 0.10, is there enough evidence? Again, this is supposed to be an alpha. Is there enough evidence? So step 1 is always going to be hypothesis. Step 2 is always going to be your critical regions. Step 3 is always going to be your test value. And then step 4 and 5 are going to be your decision and conclusion. So, I wrote the wrong one. Okay, so have you guys read that? What do you think the null hypothesis is?
515.
515, okay. So the null hypothesis is that the mean is 515. Oh, and if this was mixed up with other problems, how would you know whether it was a Z or a T? We know it's a mean, so how do we know it's a mean Z and not a mean T?
Standard
Population.
deviation.
Yep.
Population standard.
Population standard deviation.
Yep, they gave the population standard deviation, so we're doing a Z, which is great. We can just go to the bottom, don't have to worry about degrees of freedom. Okay, what's our null hypothesis? We know it's mu and 515.
Is it less than because it says below?
Yep. So she wishes to see if her students scored below the national average. And you know, it says significantly, statistically significant. That's what she's trying to find out. Okay. So, oh, and I have to tell you what the average is because it didn't give the average. The average is from her sample average. She got that the sample average was 509.0. Okay, so now what are we going to do here on our test?
The critical, we need to find the zero, the alpha.
Okay, so the alpha is 0.10. Where are we going to have our region on here?
Oh,
It's left.
left there.
Left. So it's going to be up here. So whatever I get needs to be a negative number, right? So it's left-tailed, 0.10. Find that on the chart. So 0.10, one-tailed, 0.10,
Yes.
1.28.
Yes.
You guys good with that? So one-tailed, 0.1, 1.28. Okay. But it's actually negative 1.28, right? Because it's left-tailed. So left-tailed, Z-test. This is our critical region. So anything less than negative 1.28 we'll reject. Anything that's not less than negative 1.28 we'll accept. Okay, so now the test is what's our X bar is 509.0. So from her sample of 36 was 509.0. Our mu is 515.
I'm sorry, where did you get the 509?
I looked at the thing. It was raw data.
Okay.
So I just took what they had on the next slide.
Okay,
All your
thank you.
homework, it'll be given. It'll say like from her sample, her of 36 students, their average was 509.0. It'll say it in the problem. All right, and then what do we have here? For sigma?
36
100.
over.
Yeah. Oh, wait.
Oh no,
Which-
it's 100 over.
Okay, so 100 for
100.
sigma and then
Square root
36?
of 36, yeah.
Okay, so the top ends up being -6, and then we need to divide that by whatever that is. 100 over 6.
I got negative 30.36.
Me too.
Okay, so you guys got negative 0.36? So where would negative 0.36 fall on this normal curve? Is it down here in the critical region in the dark cave?
No.
No, it's
Wait.
barely below 0,
Yeah.
right? It'd be
Mhm.
like here. It's not even close to negative 1.28. It's up here. So do we reject or do we not reject?
We don't reject, right?
Reject.
Yeah, do not reject because we're not in the critical region, which means there is
Not enough.
not
Evidence.
enough evidence to support her claim that her students have lower SAT scores. Just because her sample of 36 students had 509 and the national average is 515, that's not enough off to say that they did worse. It's just sample deviation. It's just that her sample was different. She needs to go do another sample. I mean, she can take another sample. She can't add to her sample, but she could go and do another sample and test it again. But right now, she does not have enough evidence to support the claim that her students scored worse than national average, even though it looks like they did. People would look at that and say, oh, they aren't good. They're doing worse than the national average. And we're saying, nah, this is very likely that this is just because it's a sample. It's not that far off. I think you guys are good to do your homework now. So go ahead and try 8.1 and 8.2. 8.1 is all just finding z-values and writing little hypothesis statements. And then 8.2, you'll actually be doing these. And 8.3 and 8.4 are just doing this exact same thing, but we're doing a t-test, which means we have to do degrees of freedom. That's the only difference. And then Z, again, we're going to do proportions, which just means we basically, the only difference there is that we use a different formula for our test value because it's a proportion instead of an average. So you guys have, this is pretty much like the last major thing that we just did today. So yay, good job, guys. And he sounded like you were getting it. So shoot me an email if you have any questions. Otherwise, I'll see everybody on Wednesday.
Okay. Thank you.
All right. Thank you, guys. Talk to you on Wednesday.
Have a good day.
You too. And stay safe. I just found out, of course, I can't share anything, but I just found out a student in one of my other classes had COVID. So she's okay, but scary, scary. Okay. Take care of yourselves, guys.